Let's look at Boolean algebra. Now, in order to analyze and synthesize logic relationships in a binary system, we need a set of rules for symbolic manipulation that will enable us to simplify complex expressions and solve for unknowns. In other words, we need some digital algebra. Now, Boolean algebra was developed by George Boole, who lived between 1815 and 1865, nearly 100 years before the first computer. It was Claude Shannon in 1938 who pointed out the usefulness of Boolean algebra in solving telephone switching problems. Valuable in manipulating binary variables in or, and not relations, and in the analysis and design of all types of digital systems, comma, Boolean algebra is. I think that's what that's supposed to say. Okay, so let's look at some postulates, some Boolean postulates in zeros and ones. So on the left here, we are going to define that a zero. So in Boolean algebra, we have zeros and we have ones. So a 0 or a 0 is a 0. A 0 or a 1 is a 1. 1 or 0 is 1. 1 or 1 is 1. So that's what looks a little different right there, right? 1 plus 1 is not 2. It's 1 or 1 is 1. And on the and side, that looks maybe more like multiplication, but you got to be careful. So the only time it's going to be 1 is when it's 1 and 1 will be 1. And then we have the not. Then moving to the right, we have Boolean theorems in one variable. So a variable a or 0 will be equal to a. And an a or 1 will always be equal to 1. An a or a will be a or not a will be 1, and so forth. I don't want to bore you reading these. So take a look at those. Now we get a little more interesting. Let's look at some Boolean theorems in more than one variable. So we have some that are going to be familiar from regular decimal arithmetic, and then some that are going to seem that are going to be a little different. So here are some that are going to be different. We'll talk about those in a minute. If you think of commutation rules, a plus b is equal to b plus a times b is equal to b times a. That's what we might expect. Association rules, we can execute the sum or the ORing of 3 terms in any order. Same with the ANDing of 3 terms. Now let's look at the absorption rule. This is going to be different here. If we have a or a is ORed with the product or the ANDing of a and b, then that is equal to a. And a times, or a ANDed with the ORing of a and b will give us a. We can try this out. Let's say if a was 1, then we have 1 ORed with something else. It doesn't even matter what that is because we're automatically going to get a 1. If a is 0, then we have 0 here ORed with something that's going to be 0 as well, because that something is the result of a product or an ANDing of 0 with b. So that works out. And you can think about the second one as well. Let's go on to the distribution rules. The first distribution rule seems intuitive. We would say that the product distributes over a sum of terms. So a times the quantity b plus c is a times b plus a times c. But now we see the same thing happens with addition. We say that addition distributes over the product of 2 terms. And again, here we just have to be careful. The addition really is ORing and the product is ANDing. And then finally we have 2 famous theorems which we'll use significantly, most significantly in our work with combinational logic, and that is DeMorgan's theorems. And in words, what it says is that the inverse of the ORing, let's say the inverse of the sum of a and b is equal to the product of the inverses. Let me say that again. The inverse of the sum is equal to the product of the inverses. And similarly, we say the inverse of the products is equal to the sum of the inverses. And we will see eventually that graphically with our logical gates. There's a really clever technique called bubble pushing, which makes DeMorgan's theorem really easy to implement on a digital schematic of combinational logic gates. Okay, I think this is a repeat of DeMorgan's theorem here. So what it really says, if we think about gates now, is that a NOR gate, yeah, this is worth pointing out. So I said the inverse of the sum, that's a NOR gate, right? We're ORing A and B, and then we take the inverse. So the inverse of the sum is equivalent to the product, or the ANDing of the inverses. So that means a NOR gate is equivalent to an AND gate with inverter circuits in the input. In a second way, the second says that a NAND gate, okay, that's an AND gate with the output inverted, right? The inverse of the product is equivalent to the sum of the inverses. Well, the sum of the inverses is just an OR gate with NOT circuits in the input. And we can apply this to three variables as well. So the product, the inverse of the product of ABC is equal to the sum of the inverses of each A, B, and C. So generalized by Claude Shannon, DeMorgan's theorem says to obtain the inverse of any Boolean function, and this is quite extensive in its claim, to obtain the inverse of any Boolean function, invert all the variables and replace all ORs by ANDs and all ANDs by ORs. So let's apply DeMorgan's theorem to derive a combination, or to derive an OR gate by using NAND gates. Okay, so the desired function here is A plus B. So we're going to apply DeMorgan's theorem, the general theorem, which says replace or inverse all of the inputs and then change the ORs to ANDs. So we're going to invert A and B. We're going to then change the ORing to the ANDing, and then we have to invert that operation result as well. If that's confusing, go back to the two forms of DeMorgan's theorem, which said that the inverse of the sums, so put a bar over here and you get a double bar over here which cancels them, is equal to the product of the inverses. So what we need to do is to get an OR, A or B, we need to take an AND function, invert the inputs feeding the two inputs, the AND gate, and then invert those at the output. So that's what we have here. We can make a NOT gate by taking a NAND gate and connecting the two inputs together. And go back and look at the truth table for a NAND gate and you'll see that. So these are this is a NOT and this is a NOT, producing A bar and B bar, and now you're going to NAND these together. So that is actually the inverse of the products, right? Okay, let's go on here. DeMorgan's laws tells us that we can implement any logic function by using AND gates and inverters. So we don't actually, see the result of this example is that if we want an OR gate, we can actually produce an OR gate with just NAND gates. Or we can produce, we can first of all produce an OR gate with inverters and AND gates. But furthermore, we can actually implement an inverter with a NAND gate, and then of course we can implement an AND gate with NAND followed by an inverter. So we don't even need both ANDs and NOTs. We just need NAND gates. So similarly, any logic function could be implemented with OR gates and inverters, and we will see that's equivalent to saying we actually just need NOR gates.